All right, well, I want to welcome everybody to today's Vaughn Company webinar dealing with indigestion, how to keep your digester happy and healthy. In this session today, we're going to discuss the digestion process, how mixing plays an important role in process stability, and how to diagnose and treat common digester ailments. We take all of our questions there in the bottom right-hand part of your screen, and just type in your questions there, and they'll come back to us, and we'll take most of those questions, if not all of them, at the very end. That allows Eric and Steve to get through our content with plenty of time for questions. If you are watching this on demand, or if we don't get to all of your questions, we will respond accordingly. And if you are watching on demand, just email us at info@chopperpumps.com, and that'll get back to Eric and team, and we'll follow up from there. All right, let's bring in the gang here. First of all, as mentioned before, senior engineer for Rotamix, that's Eric Larson. He's been supporting Vaughn customers since 2012. He has a bachelor's degree in civil engineering from Washington State University and is a frequent mixing and processing topic presenter. Hey, Eric, welcome, sir.
Good morning.
And let's get started with Vaughn's Rotamix manager, Steve Macomber. Steve's been in the water and wastewater industry, protecting the water environment and public health for over 20 years. Steve, great to have you back here, sir, and the floor is yours.
Thanks, Scott. Glad to be here. All right. Hello, everyone. Thanks for joining us, or thanks for joining us again for our third Rotamix seminar now. So it's starting to look like this is maybe how it's going to be for a little while. Maybe it feels a little bit like maybe a 6-month submarine deployment, but we're looking forward to it. We want to make the most of this. We really want to try to collaborate with you, our fellow water wastewater professionals, and make the most of this time. So please, we mean it. Reach out to us if you can. If you have any suggestions, or to Vaughn or to me personally, since I know many of you, let us know what we can do better to support your efforts. This webinar today is a little bit different than the previous two. We're going to dive quite a bit deeper into sort of a unit process, the anaerobic digestion process. Just a reminder that this is recorded, so if you miss anything or you get a text and you sort of don't know exactly where we are, you'll be able to find this along with our previous webinars on our website. And I do encourage you, if you haven't seen those first webinars, to check them out. They do include some important information about mixing and the costs of over or under mixing, sort of long term with capital and operations and maintenance. So with that, really want to turn it over to Eric to get started, and we'll wrap up at the end. And I hope you enjoy, and let us know if you have any questions. Eric, you ready?
All right. Thank you, Steve. So we'll just get right into it, because I think 45 minutes is going to be a pretty quick clip to go at, and we'll try to get all this information in and have time for questions at the end. So dealing with indigestion, kind of the topics we're going to cover today are really a thorough understanding of the anaerobic digestion process and the biological processes that drive anaerobic digestion, how to monitor digester performance and some of the normal monitoring that's done, and how that should inform your decisions with regards to operation, and then knowing and recognizing the common causes of indigestion and how to identify those. And then at the end, we'll kind of highlight the importance of adequate mixing and how that can really address a lot of issues related to indigestion within anaerobic digestion. So getting kind of right into it, we'll start off with kind of the anaerobic digestion process. So what is anaerobic digestion? Anaerobic digestion is a series of biological processes in which microorganisms break down biodegradable material into methane, CO2, and energy in an anaerobic environment. So generally, you're going to be, instead of using oxygen to break down and reduce these different chemical compounds down to these, methane or some other oxygenated thing, you're going to be using hydrogen, carbon, other compounds to break that down and reduce those. So why anaerobic digestion? For sludge stabilization and vector reduction, especially in the United States, where there's where the EPA has restrictions on digestion time and vector reduction targets, A lot of other nations and the EU and others have their own legislation around that. But really, it's to take biological waste and waste sludge and convert it into something that is stable, that has been reduced to something that is just nutrients and can be either land applied or reused in some way that will not create an attraction for vectors or some other danger to the environment. To reduce solids disposal volume, digestion is definitely used to minimize the amount of solids that need to be disposed of, and to reduce the amount of waste that comes out of wastewater processes. And then to produce renewable energy in the form of biogas, which is becoming more and more an important part of anaerobic digestion process, the beneficial reuse of biogas. So in the United States, at least, from a statutory requirement, the United States is basically governed by EPA Part 503. And so you've got a pathogen reduction requirement. For Class A biosolids, you need an operating temperature above 50 degrees C. There is a time component to that, but generally, for the most part, you're going to meet the time requirement if you're doing anaerobic digestion at thermophilic temperatures above 50 C. And then you've got a Class B biosolids requirement that requires a solids retention time between 15 and 60 days, depending on where your temperature is at. But generally, you're going to be operating above 35 C and around the 15-day mark for minimum retention time. And then there's also a vector attraction reduction requirement, which, dealing with trying to reduce attracting different vectors that may cause human health issues. And it's definitely a major requirement for land application of sludges, and it requests a volatile solids reduction of 38%, which is generally a pretty easy target to meet if your digestion process is healthy and operating normally. There's an active volume requirement that drives the design of digesters. With digester volume, you need to have a large enough volume to achieve your solids retention time. And most tanks are continuously stirred tank reactor designs where solid retention time and hydraulic retention time are equivalent. So whatever your inflows are for your digester, you need to have enough active volume, and that means the volume that's actively being digested and managed in that continuously stirred reactor that is staying under digestion, so that your average age of sludge leaving that process has achieved its retention time on average and has gotten the volatile solids destruction target that you're looking for. Generally you would not want to design a anaerobic digester that requires more than 90% of the actual gross volume for active volume, because you're always going to lose some volume. You're not going to have 100% active mixing throughout a tank, and that's also something that can create issues for stable operation too when you're driving a system that's operating at the limits of its capacity. So just something to keep in mind, especially for those designing. I've definitely seen, as design build continues to become more popular, a push to try to target 93 or 95% active volume, and in our experience it's just not very realistic, no matter what you're doing, to try to maintain a homogeneous state within that digester and keep that active volume there. So talk about the anaerobic digestion process. This is a really nice chart. This is from anaerobic digestion model number 1, which was put out by IWA. I believe it was made by Bestone et al. In 2002 from, I think, Queensland University. But I just really like this chart because it's not overcomplicated. It's not too graphical, but it gives a nice overview of how material flows through the anaerobic digestion process. So you can see the first step is your hydrolysis process, which kind of combines disintegration and hydrolysis, where disintegration is a physical process where things are physically degrading, and then hydrolysis is a chemical or biological process where carbohydrates, proteins, and lipids are breaking down into monosaccharides, amino acids, and long-chain fatty acids. And that process can take quite a bit of time. Next, you have the acid phase, and this combines both acidogenesis, which is the fermentation to organic acids, propionic, butyrate, and valerium acids from monosaccharides and amino acids. and then the further degradation of long-chain fatty acids into basically all of these are considered volatile fatty acids, which are kind of precursors for the formation of acetic acid and hydrogen. And then as you get to the acidogenesis phase, you're taking those volatile fatty acids and you're taking those and converting them to acetic acid, which is the main precursor for methane production. And the methane phase is just turning that acetic acid into methane with also hydrogen combining with carbon dioxide. So we'll go through each one of these steps. So hydrolysis, it's generally the rate-limiting step for anaerobic digestion. Hydrolysis without any assistance can take somewhere between 3 and 15 days to completely happen. Different substrates, though, will hydrolyze at different times. And sugar and fats generally are easily broken into monomers and long-chain fatty acids and move further on into the acidogenesis and acid phase. And that's why, you know, if anybody has a facility that's receiving fog or sugar waste from some sort of confectioner manufacturer, you know, when you add that into your system, you see an immediate increase in digestion rate and gas production, you know, on the order of a few hours. And it's because those already highly pure fats and sugars are going to hydrolyze and then could be converted into volatile fatty acids and eventually methane very, very quickly, where cellular biomass from maybe waste activated sludge processes or extended aeration are going to be, you know, mostly biomass, large cellular structures that need to be, you know, the cell walls need to be ruptured and everything to be broke down. So cellular biomass and proteins are a bit more complex and difficult to digest, and will take a little bit longer. There are technologies that are coming out which will increase the rate of hydrolysis, and they're becoming more common. We'll talk about those a little bit more later in this presentation, but something to keep in mind, as hydrolysis really is the rate-limiting step for most anaerobic digestion processes. So acidogenesis, which is generally the acid phase. Acidogenesis can take between 1 or 2 days. That's why if you ever have split phase acid then methane phase digestion, generally you're going to have about 2 days of residency in your acid phase and then a longer residency in your methane phase. And it's because that acidogenesis process happens pretty quickly. Acidogenic bacteria break down simple sugars into amino acids, and then along with the long chain fatty acids, those are broken down into volatile fatty acids, which are very simple organic acids that are very simple and easily broken into by the bacteria down into acetate. The reaction rate has positive correlation with temperature, and generally is not sensitive to pH. Generally, it likes lower pHs, but you can start to inhibit it at very low pHs. But for the most part, in anaerobic digestion, pH ranges from 6 to 7.4, you're really not going to have any impact on your acidogenesis phase from pH. Acidogenesis can be considered part of the acid or methane phase in two-phase digestion models, and I say that it's technically the acid phase, but in split-phase digestion, some of the acidogenesis is going to happen in the acid phase, some of it's going to happen in the methane phase. So it's kind of an in-between. And it's typically the fastest of the 4 steps in the anaerobic digestion process. Generally, it will complete within 8 to 12 hours rather than several days like some of the other processes. And a lot of that has to do with there's several different chemical and biological steps in breaking sugars and proteins and other things down into volatile fatty acids. And there's one step to take those volatile fatty acids and turn them into acetate. So the reaction rate tends to be quite a bit faster because it's a direct transition rather than a multi-stage transition that requires several different specialized bacteria like acidogenesis is. And yeah, we're just converting volatile fatty acids into acetate at this point for acidogenesis. And then methanogenesis, which is the kind of the bread and butter of methane production and anaerobic digestion, is really the target, and it's where it's where everything can go wrong as well. But it's the final step in the anaerobic digestion process. Methanogenesis can take between 3 and 5 days. And for those of you that have been counting, you know, you start to add these days up and it's like, well, digestion shouldn't take as long as it looks like it's taking. But really what happens is as feed goes into these digesters, it hydrolyzes at different rates, and so you've kind of got this curve of things are slowly being fed into this biological process from the hydrolysis step, and then that's really what's limiting methane production. And so, you know, you add a bunch of substrate or feed into the digester, and it's slowly taken in by the bacteria over time. But once it's taken in, these processes start, and they happen at about the same rate once you get through that initial process. We're converting in Methanogenesis, we're converting acetate into methane and CO2, and we're also further converting any hydrogen gas that's available and CO2 and additional methane. And CO2 is in the excess here. So you're going to generally convert all of your hydrogen into methane, and then you'll have leftover CO2 from the acetate to methane chemical process. You know, based on the chemical pathways, you'll find that methane is generally 90% from acetate being broken down into methane and CO2. And if you look at the stoichiometry of that, you would expect to see methane at 55% and CO2 at 45 in your gas, but CO2 is a lot more soluble than methane, and so you can sometimes see higher methane levels, and you also can see higher hydrogen production, which can also increase your methane rates. And in fact, there's been studies that have shown injecting hydrogen into a methane phase digester actually will substantially increase the methane production almost to completion. But unfortunately, in standard producing hydrogen is expensive, but also and not very cost effective. But also for the acid phase, hydrogen can inhibit the acid phase, and so there's some issues there that. But I know there's probably going to be continuing research as biogas production becomes more and more the goal. But you can see the chemical breakdown here. One acetate goes to one methane and one CO2, and then it takes four hydrogen gas. It takes 4 H2 molecules for every CO2 molecule to convert to get one methane, and then you get two water molecules. And so you can see the acetate very quickly converts to methane and CO2. It's a very strong affiliation to that reaction, and then but then the CO2 will take all the hydrogen and turn that into methane, but it utilizes that hydrogen very quickly at a ratio of 4 to 1. So happens pretty quickly, and you have a lot of CO2 left over. So THP, CTHP, and enzymes. I wanted to cover this a little bit. Thermal hydrolysis processes, THP, which are using high temperatures and pressures to lyse cells and decompose complex organic compounds. This is becoming a more common thing. There's a couple different manufacturers. Cambi's the one that we've worked with the most. And then you've got chemical and thermal hydrolysis processes, which use a strong base to achieve the same outcome at lower temperature and pressure. But generally, the longer retention and the cost of utilizing and acquiring the base to feed into the process usually lie. And so those are two different competing technologies, which are generally achieving the same thing in two different ways. And there's also supplemental enzymes that can aid in improving the rate of hydrolysis, but they're generally specialized to a certain substrate. So you might see enzymes that are designed to break down fog into long-chain fatty acids and cleave that glycerol off. And so you'll have a fog digester that's then feeding into either a blend tank or a digester that's then taking those and kind of using it to augment digestion. I've seen at least one system that was doing that. So it's something that exists, but it's generally a very specialized, highly engineered thing that isn't necessarily seen everywhere. And then pre-hydrolyzed sludges. Just kind of a note on this. This is something we've had a little bit of experience with, and we've seen some pretty positive results. But sludges pre-treated with either THP or CTHP generally just bypass the hydrolysis step because those processes act as a hydrolysis step and can reduce the time needed for digestion to really 4 to 8 days. And we've had experience with THP digesters operated by Thames Water in the UK. And according to them, the limiting factor for retention time in their digesters. These are thermophilic digesters, but the limiting factor for the retention time was really just biomass washout. They found that anything less than 8 days, and they started to wash out too much biomass, and it wasn't replenishing itself, and eventually the digestion process would stop. But it kind of reinforces that idea that really your system's being fed by the slowly happening hydrolysis process, and if you bypass that, those bacteria are just going to take off. And just, I feel like that's an important thing to understand, because it can really help you interpret digester issues, because a lot of them are dealing with how you're feeding the digester and how that feed is impacting all of the downstream processes. So I think it's a good thing to conceptually get an idea for. So pH inhibition, generally caused by the acid phase overtaking the methane phase. So if you're feeding the acid phase quicker, then the methane phase can take those volatile fatty acids and convert them, or take the acetate and convert it into methane. You're going to build up a lot of volatile fatty acids or volatile acids, and start to drop the pH. And if the pH gets too low, you can completely inhibit methane generation. So anything below 7 is generally going to inhibit methane production. And once you get below a pH of 6, the chemical pathway that methogenic bacteria use is completely non-viable. So below a pH of 6, chemically methane generation cannot happen, and methogenic bacteria can't reproduce or respirate, and they will die. Generally, though, digesters have pretty good alkalinity, pretty high alkalinity. You generally want to be above 200 milligrams per liter, which will help control pH and keep it around neutral. And but once that pH starts to drop, you're really in a bad spot. Other inhibitors: hydrogen sulfide, ammonia, long chain fatty acids if they get built up too much. So if you're putting too much fog in a digester and you're not breaking down those long chain fatty acids quick enough into VFAs, you can start to inhibit several different processes, as those can be toxic. And then salts as well. So if you have too much sodium, too much calcium, too many potassium ions, those can start to be inhibiting at very high levels. Generally, you're not going to see that unless you're using some sort of salt to supplement your alkalinity, to address some underlying issue, and deal with that, and start to build up very high concentrations of those salts in your digester. But you're really going to have to be at a pretty high concentration to see that. So it's not something that necessarily is going to be a normal issue, but something to think about if you're having issues and you're doing a lot of dosing of bases. Contaminants which have antibiotic properties generally are addressed prior to digestion. I know there's been a lot of talk about pharmaceuticals, hand sanitizers, other antibiotic things getting into wastewater flows and into wastewater treatment plants. But generally, you're going to see those earlier on in the facility. You're going to see those in your aeration process or some other primary treatment process. You're not going to see those survive all the way through your sludge handling process to get to the digester. But septage and received waste are kind of an exception to that. Septage and received waste, if there's a contaminant in a received waste that's going to go straight into a digester, and you're not testing for that, and you're receiving those things, you can definitely be causing problems for your digester, and creating issues there. And then effects of temperature. There's two main temperature ranges for anaerobic digestion. You've got your mesophilic, which I've got Fahrenheit here because the chart's in Celsius. So 95 to 105 degrees Fahrenheit. Generally, you'll see mesophilic digesters operate between 98 and 100. And if you look on the chart here, you can see that that 35 to 40 degrees C is really, which is the conversion, is really the sweet spot for mesophilic bacteria. And you can see you get above that and it drops off very quickly. And then for thermophilic, you're 120 to 145. And really, I think it's 122 is 50 degrees Celsius, which is the thermophilic minimum temperature for regulatory reasons in the U.S. So generally you'll see 122 to 145 degrees Fahrenheit or 50 to 60-ish C for thermophilic digestion. Thermophiles can handle 63, 64 degrees C, and anything more than that, unless it's a specialized bacteria, which generally you're not going to see in anaerobic digestion, you're going to start to see that drop off. And I think the key here is these bacteria are sensitive to temperature, but they're also sensitive to temperature changes. And anything more than about a degree C per day in temperature change can create issues and start to inhibit biomass growth. And also, you can't take a mesophilic digester and then just change it to a thermophilic digester without changing the biomass in the digester. If you try to do that, what you'll end up doing is you'll kill off your mesophilic bacteria once you get above about 45 C, and then you won't have the thermophilic population to build a thriving methogenic thermophilic methogen biomass before the acid phase just completely sours the digester. So if you're looking to change where you're operating, or you're looking to, or you notice that you've been running at lower temperature and you want to increase it back up, you need to make sure that you're not making rapid changes and that you're slowly getting back to whatever that temperature target is for your facility, and addressing that slowly. I think as we get through today, the underlying message is going to be digesters they don't like change at all. So anything you can do to make your process more uniform and stable is going to improve the health of your digester in general, and that applies to just about everything. So monitoring digester performance. Generally, there's a few monitored parameters in every digester. These are going to be the things that are listed on your SCADA that everybody's got access to and are going to be logged on a regular basis. So your feed and waste rates, these are required for reporting, at least in the U.S., and are going to be monitored through flow meters and sampling from the lab. You got temperature, pH, biogas production and composition, volatile acid and alkalinity ratio, and volatile solids reduction, and volatile solids reduction. I thought I had one more, but I guess I didn't. Oh, I combined feed and waste. That's what it was. But these are generally the parameters that you're going to be monitoring in almost every facility, and we'll talk a little bit about each one in more detail. So temperature, it's a continuous monitoring. It's generally measured at inflow and outflow of the heat exchanger system. So you're going to have something that's measuring the temperature of sludge that's entering your heat exchanger loop, and then the temperature that's leaving. If your temperature measurement is inaccurate, it can definitely reduce digester performance, and it can be inaccurate for more. It can be inaccurate even if your probe is reading correctly. If you're short-circuiting the heat exchanger loop because of poor mixing or other issues with placement within the tank, you might be reading that your temperature is right on the money. Your target's 102 degrees, and you're getting 101 into the heat exchanger loop, and you're running that at really low temp and getting 102 out, and everything's really happy. But in reality, you're short-circuiting that system, and the rest of the digester's at maybe 92 degrees and not within a good range. So it's something that you can check every once in a while if you feel like you're not sure you're getting correct measurement by doing a temperature profile test and taking a temperature probe and dropping it through a thief hole or some other sampling port to get a good feel for what temperatures look like throughout the digester. pH, also continuous monitoring. Generally, you'll see combined temperature pH probes, or you'll have pH probes throughout sample points in the digester and also on samples that are being taken for lab testing. Generally, it's a lagging indicator of digester performance, though. And the reason for that is healthy digesters have good alkalinity levels and will buffer changes to pH pretty strongly. And so, by the time the pH is changing, there's already been a significant change in the chemical composition of your digester. And if pH is dropping, usually it's too late for intervention in a meaningful way. So biogas production composition, again, another continuous monitoring. Generally, you'll have a probe in either your gas collection system or maybe even in your headspace. Many different levels of meters. In terms of complexity, generally you're going to be monitoring CO2 and hydrogen sulfide, but sometimes you'll have hydrogen as another measured gas. And methane is usually a calculated value, which I don't know if a lot of people are aware of that, but there are absolutely meters that or probes that actually measure methane composition. But a lot of older facilities and older probes, you'll be measuring. It'll actually be measuring CO2 and then assuming that the rest of the gas is methane. And so it'll take your whatever the it'll take whatever the total gas production is, take out the CO2, and then calculate the methane from that. And this actually was kind of funny. I had a friend who was sitting for his level 4 operator license, and he had a question and I was kind of helping him out with it. And he asked me what I thought, because the facility he was working at had a CO2 meter, and the question asked, you're seeing a change in gas production. What should you look for in your gas composition? And he would always look at the CO2 because it would inform him on the methane. But the answer they wanted was methane, because the meters in most facilities read out methane, but his facility just happened not to. So it's kind of an interesting thing, but as things continue to be improved, though, most meters are measuring all four: methane, CO2, hydrogen sulfide, and hydrogen, and they're all important for various reasons to know those concentrations. Volatile acid alkalinity ratio. This one's, I think, kind of the unsung hero of trying to determine digester health. It's a discrete sampling data point, as far as you need to take individual samples and take them for lab analysis in order to calculate the volatile acid and alkalinity. Generally, facilities I've seen like to do three a week, generally Monday, Wednesday, Friday. But some facilities do it once a week, some facilities do it every day, and some facilities never do it. And I don't believe it's actually a required analysis in the United States for reporting, but I absolutely recommend it as something to monitor digester health. You generally want to have alkalinity over 2,500 milligrams per liter, and your volatile acid alkalinity ratio below 0.01. And we'll kind of cover that, and this is what our questions are going to be over today, and it's an important indicator of digester health. So we're going to consider the following. So everybody kind of study this chart. You can see over the course of about 2 weeks, so this facility would be sampling 3 times a week. And you can see over the last 2 weeks, the volatile acids have been slowly creeping up from about an average of 300 milligrams per liter up to about 500, and the alkalinity, which was at a very nice 3,300 milligrams per liter, is now dropped to about 2,200. And you can see at the beginning on May 18th, the ratio crossed 0.1 and is now above 0.2. So considering that, what impact would you expect to see on the pH value of the digester from your pH probe? Would you expect it to increase, to decrease, or to stay the same? Oh, I lost there we go. Stay the same.
There we go. So
we'll give everybody.
So Eric, we've put the poll up there on the screen for you guys, everybody, to kind of go in there. Should we? You want to look at that chart one more time, Eric, just to help people out?
Yeah, we can
sneak back a little.
Yeah, so we'll leave the chart up here. So I'm seeing about the answers I expected to see, and
how about if I share those results with people?
I think, yeah, we'll go ahead and share the results. So in reality, you're going to see them likely stay the same or essentially the same, and the reason for that is you're going to be consuming that alkalinity, which is going to buffer your pH back to neutral, and as long as you have sufficient alkalinity to buffer the increased volatile acids, you're not actually going to see your pH drop. And that's why I really want to reinforce that if you have good alkalinity, you're not going to see significant change in the interaction between your acid and methane phase within your digester. And so by the time you see a change in pH, your alkalinity is consumed, and there's really, you're already so far gone that you're going to have a really hard time bringing that back into balance. But I don't want to say that the people who chose decrease are necessarily wrong either, because you might be at 7 and now be at 6.9 or 6.8. You'll see a slight drop, but generally it'll be about the same. And so moving on to the next slide, what actions will not improve the volatile acid alkalinity ratio? So we got decreasing feed rates, increasing feed rates, introducing sodium carbonate, and introducing calcium carbonate. And I think this one's probably the easier question. We've got the poll up again. Thank you, Scott. And we'll let this one go. For those of you in the operations field, this one's probably going to be a real common one for you, and probably something you've had to deal with. For those on the engineering side, I'm not sure if this will be as intuitive, but I think we've got a decent number of answers. So Scott, if you want to show the results on that, and I'll show the answer. So as we can see, most people chose B, increasing feed rates, and yeah, that's absolutely right. So if your acid phase is overtaking your methane phase and producing more acid than methane phase can deal with, one of the best ways you can deal with that is either to increase the alkalinity and address the additional volatile acid production, and sodium carbonate and calcium carbonate are both going to act as alkalinity, are going to provide alkalinity and buffer that pH, or decreasing the feed rate and slowing down the food that's going into the acid phase, and slowing down the ability for it to convert that feed into volatile fatty acids, which are going to increase your volatile acid number. So you can either shrink the numerator or increase the denominator, but increasing feed rates would obviously increase and spike VFA production and just make your matters worse. So hopefully that woke everybody back up, but I think that's a really good example of why I think volatile acid alkalinity ratio is one of the more important things to be monitoring, because it will give you, even though it's not a continuous instantaneous measurement, it will definitely provide you with the feedback that you need to understand whether your process is staying stable or if it's starting to become unstable, and give you a little bit of warning before things become dire. But again, if you are using sodium carbonate or calcium carbonate on a regular basis to deal with a digester that is not balanced, and you're having to keep adding buffering and alkalinity into that digester, eventually you will get to salt concentrations that will start to inhibit your biomass growth, and you won't be able to fix it by adding more alkalinity. So now go to the next slide. And then volatile solids reduction. It's calculated from feed and waste sludge volatile solids ratios. I'm sure most people are familiar with the Van Cleek equation, which is just, it takes your volatile solids in, volatile solids out on a percentage basis with total solids, and calculates out a volatile solids destruction. This is generally the main metric you hear when people describe digester performance. They'll say, well, what do your volatile solids destruction look like? How much volatile solids are you getting rid of? And that's generally seen as, well, your digestion process is going really well if you're hitting, mid 60s in terms of 60% volatile solids reduction. And in the U.S. at least, there's a target of 38%. And if you're not hitting that 38%, or even getting to 50, it's seen as something's wrong. So that's something that you can definitely follow. And it provides a good background trend line. If you were digesting and hitting, a volatile solids reduction of 60%, and then all of a sudden you're only hitting 50%, that's usually a good sign that something's going on and that you need to do a further look at what's going on in your digester. And then mass balance. This is calculated for feed and waste sludge data as well. And it's really a check on all of your other measurements to verify the accuracy of measured values. Your mass in if your mass in doesn't equal your mass out plus your volatile solids reduction, this can be a sign of poor operating conditions. And one of the biggest things is all the Van Cleek equation in particular assumes that any inert solids or inorganic fraction that's going into the digester is leaving the digester. And if you have poor mixing or are not or don't have a good active volume and you're seeing deposition, you will see volatile solids that are considered destroyed because they've become deposited in the bottom of the digester, and then you'll also see inorganic material also depositing and leaving. And so your Van Cleek might say that you're just seeing worse volatile solids destruction or about the same volatile solids destruction, but in reality you're not destroying those solids, they're building up in your digester. And a mass balance is a good way to verify that that's not happening and to check that. And so you'd want to look at what's my mass of solids going into the process, what's my mass of solids coming out, but also looking at is my inorganic total solids going in equal to my inorganic total solids coming out? Because if it's not, you're losing some in the digester because it's not being digested. Something else is happening. So that's a good thing to keep in mind. And then I see a lot of questions coming up. I'll do my best to address those at the end. I don't have a good ability to kind of stop and go and take these questions as we go. But please keep asking questions, and at the end we'll go through them and hopefully be able to answer questions that are there. So what is indigestion? Indigestion is a disruption of the anaerobic digestion process. So indigestion is going to be anything that upsets that anaerobic digestion process and stops the biological functions that are happening that are moving that process along. The disruptions can be either physical or biological, and then it can cause reduced volatile solids reduction and biogas production, and that's generally where you'll see it. I think it's generally if you're seeing your gas production numbers drop or you're seeing your volatile solids destruction drop, that's going to be because that process is no longer moving along, and I'm kind of deeming that indigestion for the purpose of this presentation because I think that's just a good word for it. And then you can have other operational issues like foaming that don't necessarily cause problems for volatile solid destruction or biogas production, but cause issues for just operation of the digester. You overtopping, bulking, other issues like that aren't necessarily hurting the rate of the process, but are hurting your ability to manage it. So one of the biggest ones is non-uniform feed. Inconsistent loading or high-strength feed sludge can upset a digester, most definitely. Inconsistent feed spikes the production of VFAs, and it consumes alkalinity and inhibits methane production. And so when we talk about feed, most of what you're feeding into your digester is going to take quite a while to hydrolyze, but there's going to be a certain portion of it that's going to hydrolyze immediately. And those materials are going to immediately be converted to VFAs, and you're going to see that you can see issues within an hour of feeding sludge in terms of changes to your methane production, because the additional volatile acids are limiting, before they can be buffered, are restricting methane production. You'll see methane production drop and volatile acids spike. And so, and if that alkalinity is consumed, that pH will drop and the methogenic biomass will be unable to produce methane. And so if you're adding a giant wad of, sugar waste or fog or some other high-strength waste, you could add enough that you consume all of your alkalinity at once, especially if the amount of high-strength waste compared to regular waste is a pretty sizable fraction of the total waste going into the digester for feed. And if your digester isn't used to seeing those kinds of substrates come into it, you can definitely overwhelm the biomass pretty quickly. And anybody who's received high strength waste or septage into a digester, I'm sure you've seen it in your lab data that it can have a pretty instant effect on digester operation and methane production. So the best thing you can do is manage your feed rates. Digester feed rates are ultimately driven by facility loading. Totally, the number one problem with wastewater is you don't know what you're going to get or when you're going to get it, and you just have to be ready for it. But managing how that moves through your process is the best way to manage the feed rates. But ultimately, you don't have control of what you receive for the most part. Continuous feed is best when possible. If you can be continuously feeding into your digester, that's going to provide the most consistent situation for that digester. The biomass gets to a nice equilibrium. You've got the same amount of food going into the same time consistently. It's being broken down at the same rate through every step in the process, and everybody's happy. And once that gets settled and in equilibrium, you can get a very efficient digestion process. But it's not really possible for all facilities. A lot of times you're going to be getting sludge from various processes at different times, and it's all going to be coming at once. But anything you can do to provide multiple smaller feed cycles is going to be better than larger feed. And not all feed stocks are equivalent. Measure the volatile solids percentages in your primary and your WAS. Measure anything coming in as best you can, and try to blend those to get a consistent amount of feed going into the digester at the same time. Don't send all your primary in the morning and all your TWAs at night, because you're gonna see unbalanced digestion happening, and it's going to have an impact on your biomass regeneration and your digestion process. And then so balancing that sludge loading is really good practice. And you can feed really high strength waste regularly to a digester. In fact, you can run a digester on only high strength waste, but you need to help the biomass acclimate to that type of operation and make sure that they're capable of handling that, because if you just try to go into it right away, it's not going to work. And blend tanks can also equalize feed rates. So if you have batched feeding of sludge into your solids handling process, blend tank not only can help blend that so you can equalize the feed strength going into your digester, but it also can equalize your feed rates if you have the capacity in those blend tanks to do that. And so really it's a best practice if you have the capacity and the funding to add that to your facility. Definitely will help stabilize digestion and get a better digestion product, which can also save money, especially when you look at the consistency of your dewatering and the quality of your dewatering cake. Inhibition, contamination, introduction of contaminated waste, elevated ammonia levels, high concentration of salts. The solution to these is dilution. You want to try to reduce the loading into the digester and allow the concentration to reduce. But I will say, these are also things that, depending on how bad you're talking about, I saw there was a question about what level what level are you going to see inhibition, and the answer really to that is any level that is significantly above what your digester's used to. There was a nice study that was done, and I don't have it off the top of my head, but there was a digester that was taken to an ammonia level of almost 8,000 milligrams per liter. That was no longer that they slowly raised it up to that level, and they were able to get good digestion rates at ammonia levels that high. And it was basically they looked at the biomass and saw that they had several ammonia tolerant species of methogenic bacteria that had taken over the methogenic process and were able to operate at those high ammonia levels. So there isn't, you don't want to make any significant changes, and there's definitely a limit where you're too much. But the idea is really just to maintain things at a consistent level and not change them significantly at any given point. And in some cases, you might see tertiary treatment. You can see ammonia being removed from the liquid fraction of your dewatering process. There's several processes to do that. You can see ammonia being removed through nitrogen removal processes in tertiary treatment before digestion. You can definitely add chemical buffers to address salt formation and get those to precipitate and precipitate those out. There's various different things you can do if you know what you're dealing with, but identifying it is generally the biggest issue. And then non-uniform temperature reduces rate of digestion, and small changes in temperature can stress biomass even if the temperature is within optimal range. Temperature correction should not exceed 1 degree C per day, and realistically, you don't want to see a variation among your digester volume of more than 1 C, because it's as sludge moves throughout your system, it's going to encounter those different temperatures and cause issues. Non-uniform solids content reduces biological contact, creates varying conditions within the digester inhibiting biomass, and there's an inability to maintain optimal operating conditions because the biomass isn't getting the food it needs at the time it needs, and you'll start to get concentrations of various different substrates from different steps of the process that may be inhibitory to other steps in the process if they're in too high a concentration. Similar to VFAs, if you get too much VFA production in a certain region of the tank, and you start to have that build up, you're going to not see any methane generation in that side of the tank, which is going to consume those VFAs and acetate, and so that can create some problems. And it'll cause unstable digestion rates, but also if you have a slug of flow in your digester that has finished one step, but it doesn't have the biomass to do the next step, and then all of a sudden it encounters that biomass, like you have a mixing system off and you turn it on, you may all of a sudden reintroduce that biomass to this available feed, and it will happen all at once, and that's where you can get into foaming and rapid rise and other issues. And you can see that where somebody might have a digester that they feed, and then they don't run this mixing system for a while because they were having foaming issues, and then they turn it back. Then they turn it on 12 hours later, and all that feed gets hydrolyzed and consumed and turned into methane all at once, and it creates an upset. So something to think about. So the importance of adequate mixing. Mixing maintains stability. So it creates homogeneous digester volume for the biomass. It provides consistent pH and temperature, and it reduces deposition and loss of digester volume. It's all about maintaining consistency and homogeneity within a digester. That's how you reduce the chances of indigestion, is to maintain a stable process that is not changing over time, that is consistent for the biomass, so that they can get to a happy equilibrium and function at their optimal levels. So talk a little bit about Rotamix here before we get into the questions. Vaughn is a manufacturer of a mixing system technology, and we want to talk about that a little bit. So it's a hydraulic mixing system using fixed nozzles and an external chopper pump. And the Rotamix Design is a multi-zone mixing which creates even flow across the tank diameter. We use multiple discharge points to create an even distribution of solids within the tank. And we use CFD, computational fluid dynamics, to model our mixing system designs so that we can match the mixing system to the process and make sure that it's providing the type of mixing needed to help that biological process move forward and provide a stable digestion rate. And CFD is really the most dependable way to model mixing system design performance before you build something, which is the goal always. So why use Rotamix? It's a reliable, effective means of mixing. It has flexible designs for all geometries and process applications. No moving parts or maintenance inside the tank. The unmatched reliability of Vaughn chopper pumps. And each mixing system design is optimized by CFD. So with that, we'll get into the questions. I know there's a bunch of process questions, and if you have anything else, please add it. If I went a little bit over, and I apologize for that, I'm willing to stay on and answer questions as long as you're still available. But if there are any questions we don't get to, I'll do my best to reach out and respond to those.
Sounds good, Eric. This is Steve again.
All right.
Add one more thing. In the interest of everyone's time, we'll make this very quick. Long story short, we just want everyone to know that we have the depth to partner with you. We're not just an equipment manufacturer. We want you to know that we have water, wastewater professionals on staff. So please partner with us. Ask us for references. We've got 2,500 at least of these installations out there, so chances are very high that we've seen something similar to whatever you're working on. We're happy to just share our experiences with you, let you know how we created stable processes in each of those cases. So with that, ready to question and answer. I think, are we ready for those, guys?
Yeah, let
Let
I'm
me
ready if you're
point
ready.
out real quick what's on the screen here while we get our questions queued up and Stephanie back on the line here. We've got all kinds of resources, links to our website, some great videos here. We talked about a participant certificate if you would like one of those for your records in participating. This is some great information, very detailed. Excellent job, Eric, by the way. Down in the bottom in there, in the other resources box, if you click participant certificate or any one of those, but participant certificate specifically, and click browse to, that will bring up a new screen and area to fill out your information. If you are listening to this on demand as a recorded session and you want access to any of these resources or have other questions that Eric doesn't get to here, just email us at info@chopperpumps.com and we will get back to you. All right, guys, I'll turn the floor to you. Stephanie?
All right, great job, Eric. Thank you very much. Thank you, Steve. The first question I'll answer real quick. As Scott said, that the on-demand version will be available on our website, but if you do want just the PowerPoint slides to have, those are also available. Please just send an email to info@chopperpumps.com and we will make sure that you have those very quickly. All right, first question here from Jonah. I know that fogs and fogs and other more simple sugars break down easier than more cellulosic feedstocks like manure, but I've heard that fogs and these more simple sugars actually improve the breakdown of the more cellulosic feedstocks. Is this accurate?
You know, I don't have any information to confirm or deny that, but I know that you know, when you talk about cellulose, you're really looking at cellulase to break that down, or just time and temperature to physically degrade it, and so that's a challenge for a lot of processes that are seeing grass or hay or some other very high cellulose containing material, and there might be some relationship between the breakdown of volatile fatty acids and the support of cellulase production or cellulase concentrations, but I don't have anything to support or deny that right now. So, but that's a really good question. I'm definitely going to do some more research and look into that.
Okay, Akash asks, what are some examples of these complex organic compounds that require THP or CTHP?
I don't think that anything requires it, but for example, waste-activated sludge is going to make up a large percentage of sludges into a standard anaerobic digester, and especially with an extended aeration process, you're going to have a lot of aerobic bacteria biomass that, you know, you're taking all of these organic compounds and they're being consumed and then turned into biomass, and that's kind of the idea behind an extended aeration system. And then that biomass is then going to go to a digester. Well, all those cellular walls, all those aerobic bacteria and the biomass, it has to be broken back down into those simple sugars, amino acids, proteins, the like. And in order to do that, you know, those cell walls are designed not to easily break down, and so that can take some time. THP, CTHPs tend to lyse those cells and improve the rate of that, and also the rate of degradation of other processes. It really just kind of reduces everything down to very simple compounds. But it's not necessary, but it's something that, you know, if you're looking to increase the rate of digestion, it's definitely something to consider, although they are fairly expensive processes to install from a capital side and also from an operational side. So, you know, it's not a one-size-fits-all application, but it's something that definitely is becoming more popular, so I like to touch on it.
Okay, Thomas asks, what is max total solids level you can sustain with mixing?
So we can do total solids up to about 12%, depending on what it is we're mixing. Above that, you start to not be liquid anymore. You start to be more of a solid, and you start getting into solid things, solid processes like composting or solid digestion, which is not an area that we work in. But realistically, whatever you feed into your digester, the actual operating total solid level of that digester is generally going to be about half of that, because if you're feeding 8% sludge that's 70 to 80% volatile solids, and you're reducing that on average by 50 or 55%, the volatile fraction of that, you're going to see that 8% sludge quickly become a 4.5 or a 5% sludge in terms of what you're actually mixing in the digester. So for example, THP processes generally are feeding 10 to 12% solids, but the actual sludge that's being mixed is somewhere around 4 to 6% solids. But the rheology is different for every different sludge. So we do a lot of rheology testing to plug into our CFD analysis for the mixing systems to look at exactly what we're mixing and make sure that we understand the concentration. And we'll tell you if we can't mix it, but generally most things you're going to see in a digester we can mix.
Okay, Rob would like to know, can you add Rotamix to an existing digester?
Absolutely, and there's a couple different ways we can do that depending on the digester. Generally what we'd like to do is when the digester's offline for a clean out, make the capital upgrades and add Rotamix, and we can take a look at existing design and existing sludges, get the rheology from those sludges and do an analysis of what improvement you would see in terms of active volume and flow rates within the digester for a mixing from a mixing standpoint. But we also have the ability to add supplemental mixing assemblies to digesters depending on the availability of access points to do so. If there isn't the funding or the ability to take that system offline, and there's an interest in trying to supplement mixing, we can also do that in some cases. So it's always something we're happy to talk about.
Next question's from Carl. When feeding fog, what do people do to prevent it from floating to the top and forming an accumulating Crisco-like layer on the top?
I think you just need to have good mixing. The idea is you want to be feeding fog at a location and at a rate where it's going to have time to process before you'd see it at the surface where it potentially could crystallize. You want to be operating the digester at temperatures where you're not going to see fog wanting to come out, wanting to solidify, and generally you want to have good enough mixing that you're addressing the surface of the digester in a direct way and not just relying on the flow of the mixing pattern of the digester to address those floatables. You want to be directly addressing those through targeted mixing.
No, we've still got more. We've still got more.
Okay, we'll keep going.
These questions are just popping up like crazy now.
Yeah, there's more coming in. I see them. All right, well, I'm ready for the next one.
Joan asks, which is the best way to agitate with Rotamix? Continuously 24/7 or with on-off? Which indicators we should follow to decide each strategy?
That is an awesome question, and the answer is every Rotamix system is designed to be operated 24/7. For digesters in particular, we recommend having a variable frequency drive that can change the mixing energy, because the system is going to be designed to reduce deposition and settling as well as maintain a homogeneous condition for the biological process. And generally the biological process doesn't need as much mixing as keeping solids in suspension does. And so we'll generally recommend that the facility look at if you can provide the minimum energy per day, if you can provide full energy for a minimum amount of time, generally about 2 hours a day. 2 hours is enough time to get it up to speed to resuspend anything that might want to come out of suspension. And then the rest of the day, you can operate it at a lower mixing rate, which is the minimum needed to maintain the biological process. As far as on-off goes, you can definitely run a Rotamix on-off, and you can find a stable way to do that, especially if you don't have a VFD and you only have on or off as your operating states. But I would recommend for maximum digestion that you run it on most of the day. I will caveat that with, though, if you've been running it on-off, don't go straight to trying to run it on, because you're going to change what you're going to change pretty drastically what the condition in your digester is like, and your biomass might not be able to handle that. You should always do very small changes. And if you've got, if you don't have continuous feed and you're feeding at various points in the day, you might not necessarily benefit from having it continuously on, and you might want to have your on-off around your feeding times. I see that as a very common way to use the systems. Not necessarily my recommendation, but for a lot of people, it seems to be working well for them. And so I always have a thought of if it ain't broke, don't fix it. But hopefully that provides a little bit more context. And if you have a system in particular that you're interested in looking at and trying to optimize, I'd be happy to work with you offline to look at that and try to make a recommendation or at least point you in the right direction, because generally the person operating the facility knows way more than we will ever will about their system.
Okay, we're going to go ahead with one last question. If we didn't get to you, then we will certainly reach out to you in an email. But last question from Joaquin. If we use Rotamix, how much less air is needed if we normally use aeration systems in an anaerobic digester? In an aerobic digester, I'm sorry.
So if you're Gotcha. So for aerobic digestion, generally, and especially if you look at design specifications and design guides, you'll see there is a calculation for what the required oxygen level is. So there'd be so many pounds per day of oxygen required to drive the biological process, and then there'll also be a pounds per day or a SCFM requirement either per square foot or per cubic or per square area or per volume needed for mixing. And the idea is that if the mixing number is above the biological process number, that you'll provide additional aeration to mix. What we found is generally in aerobic digestion, that mixing number is 2 or 3 times higher than the actual required oxygen for the biological process. And if you use a Rotamix system in that to provide the mixing energy and only focus on the biological oxygen requirement, you can use significantly smaller blowers, significantly less diffusers, and operate a system that may not necessarily you might see the same amount of installed horsepower or maybe a little bit less. But as far as your ongoing capital and maintenance costs go, it's definitely cheaper to maintain a Rotamix system than it is to maintain, a 100 horse blower compared to a 40 horse blower. So that's something that we're definitely working on with a couple different customers and trying to get some installations installed. But we have installations installed that have seen great success, and we're very interested in continuing to explore that market as we move forward. But I definitely think there's a great opportunity there to provide a better mousetrap.
Steve, you want to jump in and add anything else on that discussion?
I just wanted to add that last point. That's a very hot topic right now. Is the motive force reduction that we can provide combined with air in different unit processes, not just in digestion. So that is something that we're studying aggressively. We have installations, but there's a lot of interest with academia, and it's a very hot topic. So to be continued there, but please reach out if you have questions about that, and we'll continue to push that concept forward. But there's significant savings opportunities there with the cost of air and electricity involved with adding air is the most expensive part of the process. So stay tuned.
Yeah, and I think that might be in the near future a topic for a future presentation as we get more information together and start to compile some of our research that we've done. Definitely something probably to look for in the coming months.
Very good. Stephanie, is that the end of our question time and list and whatnot?
I think it is. Super job, guys.
All right. Well, thank you, Stephanie, for walking through those. And if we didn't get to your question, or you have more questions, or you're catching this on demand, just email us at info@chopperpumps.com. All right, Steve, any last words before we close down for the day?
just want to thank everyone for sticking around. And we went over a little bit on the time. Sorry for that, but we appreciate you staying with us, and look forward to continue the conversation when we can.
All right. And Eric.
Yeah, thank you, everybody. This is always a fun time. I appreciate all the great questions and look forward to answering the ones we weren't able to get to in the coming day or so. And I look forward to having you again. We've got Foaming at the Mouth coming up in the next couple weeks, and I'll be back for that. So looking forward to it.
And it'll be right in the same spot. So if you haven't registered yet, you can do that at chopperpumps.com/education. You can click the link right on the homepage. And with that, we will close the book on today's webinar. Thanks again to Eric and Steve, Stephanie, and the whole Vaughn crew. We appreciate everybody's participation in today's session, and we will see you at our next webinar. Thanks again, everybody.
Thank you.